My name is Asher Brohart, and I will be presenting a research paper on auroras. Auroras are a naturally occurring phenomenon that happen around the North and South poles. They are patches and patterns of glowing light floating in the sky. And depending on where they are called, where the aurora is, if they're around the North or the South Pole, they're either called Aurora Borealis around the North and Aurora Australis around the South. And also, aurora is the Latin word for dawn. The Earth is like a giant ball with a bar magnetic with two poles on either end, and it has a relatively calm magnetic field, just like any other magnet. However, the sun has a different story. The sun does have a north and south pole like the Earth, and it does have a magnetic field, but it has other parts and polarities that cause disturbances in the magnetic field and tear holes in it, and this creates lots of eruptions from the sun's surface, like coronal mass emissions, solar flares, and other things. Now, these eruptions, they spew out a bunch of electrons and other charged particles into the. Now, these electrons and other charged particles are accelerated towards Earth by solar wind, and this solar wind is this solar wind, as shown in the diagram, goes towards Earth, but then the magnetic field blocks it, so some of the particles are just get pushed away, but then other particles follow, because they're electricity, they follow the magnetic lines of the Earth's magnetic field towards the poles, and this this works like a neon light. If the electricity follows the magnetism to the poles, where it collides with gas molecules in the atmosphere, and these gas molecules become excited until they start to glow various colors. And now, during this process, not only creates the auroras, but it also creates the ionosphere, which is where the auroras occur. Because whenever the electrons come down to Earth's atmosphere, they can either latch onto other atoms, giving them a negative charge, or knock off electrons off of atoms to give them a positive charge, and this turns them into ions. Now, different gases at different altitudes glow different colors. So oxygen, which is like the most dominant gas in our atmosphere, or one of them, nitrogen is the most dominant, but it's up there with where the auroras occur, about 60 miles above the Earth's surface. And when it's that high up, it produces this blue, this green and yellow color, kind of similar to what's shown here. And since there's the most oxygen, and that's where auroras normally occur at that altitude, and that's what we see the most often. However, at higher altitudes, about 200 miles above the Earth's surface, they become these red auroras, which I'll show you in a moment. But first, I want to tell you that there's also nitrogen in our atmosphere, and nitrogen produces a reddish purple light. But if the nitrogen's been ionized by the electrons coming from the sun, then it'll glow a blue light. And you can kind of see purplish red. And I'm just going to tell you, the most common form that auroras are seen in are the curtains. But the curtains can stretch out to become these arcs, like shown in the picture. And I think those are some curtains over there. But these arcs are the most stable form of aurora, and they can go for hours without changing. However, around midnight, during the peak of what is called an auroral storm, which is what was happening whenever the sun spews out particles towards Earth, that's a geomagnetic storm, which causes these auroral storms. And the auroral storms, they can, during the peak of them, these arcs can start to bend and sway rapidly, and and change altitudes and colors, and they just look really pretty. Now, this is that red aurora. One more thing that auroras can be also, so they can be in currents and arcs, they can also be in clouds. So this is more of a cloud-formed aurora. And like, even though they're so active, usually by morning they're nothing more than flashing clouds of color. But how did auroral science start and progress? Well, in the early 16th and 17th centuries, natural philosophers, or what we would now call scientists, thought that these were caused by polar volcanoes, and others thought they were just optical phenomenon like rainbows or halos. And when Galilei saw these, he thought it was just sunlight reflecting off the upper atmosphere. So he called them aurora, which is, as I said earlier, the Latin word for dawn. Now, even though this theory was later proven to be wrong, the name stuck. In the article, Nature's Most Spectacular Light Display, tracking the Aurora Borealis in the newspaper Weatherwise, Volume 17, Issue 3, Jack Williams wrote, "The first step toward today's understanding came in 1716 when the English astronomer Edmund Halley related northern lights he saw from London to Earth's magnetic field. Other observations within a few years confirmed this." End quote. And then later, Jean Jacques de Marie proposed that interactions between the sun's atmosphere and the Earth's atmosphere caused auroras, which was actually pretty accurate. Now, the world's leading electrical scientist, who I'm all sure you have heard of, Benjamin Franklin, suggested that auroras are electrical discharges, and even though both scientists were correct, Benjamin Franklin and Jacques, their ideas were far ahead of their time, and so they weren't really taken into that much account until later. However, when the telegraph was invented in the 19th century, that put a new aspect on geomagnetic storms and auroras, because you could sense whenever they were happening. Because the telegraph operators, they would get shocks because of the electrons in the Earth's atmosphere. They'd get shocks through their machines. And these shocks could be so bad that they set the paper on fire and just started fires. And they could be dangerous. But the telegraph operators started to realize that these shocks were related to auroras, but they didn't really know how. They just knew that they happened around the same time as auroras. And this, Mr. Richard Carrington provided robust evidence for this, and that was when the Carrington event happened. But I'll get into more about that later. William Thomson Kelvin, who was also known as King Kelvin, was skeptical though, but for good reason. They didn't really have a whole lot of evidence suggesting that this is actually what caused it, but he soon ran out for that excuse. However, his opinion did affect many of the world's scientists, and for a long time, there was different scientists thought different things about what caused auroras, and they weren't really sure what to believe yet. But by the 1900s, they had gathered lots of information that the geomagnetic activity and the sun's solar storms and auroras and all of that was all linked together. Jack Williams wrote, "One of the major results of Kelvin's reaction of solar influences on geomagnetic storms and auroras was to slow global acceptance of the pioneering work of Norwegian scientist Christian Olaf Birkeland, who used observations, laboratory experiments, and various hypotheses in the early years of the 20th century to develop a theory explaining how solar activity causes auroras." Now, later in the 20th century, more observations were made that led to further studies, and these were made whenever the radio was invented. Now, one thing I noticed about this is that whenever someone comes up with a new way for communication that involves electricity, then you start getting side effects caused by the sun and the auroras. And I thought that was interesting. Anyways, observations confirmed his ideas on how auroras were caused. Now, the inventor of the radio, Guglielmo Marconi, sent a signal across the Atlantic. He realized that the Atlantic was a very far distance and that there was no way that the radio waves could have made it that far without bouncing off of something. Remember that ionosphere I told you about earlier? That's the culprit. The radio waves can bounce off the ionosphere to elongate their range. And he shot the radio beams and it bounced off the ionosphere and it went across the Atlantic. So, however, the ionosphere is created by solar energy, and solar activity can change its properties, which is how you get the auroras. Now, this knowledge was incredibly useful during World War I and World War II because they could use it to send radio signals all over the world. Now, earlier I mentioned the Carrington event, but what was that? On September 1st, 1859, Richard Carrington was sketching the location of sunspots on the sun. Now, he was, at the time, sketching a particularly large, unusual group of sunspots, when suddenly, as he was looking at it, two bright dots of white light appeared around the sunspot group. And there was a very bright flash of light that lasted for about 5 minutes before it was gone. Mr. Carrington had just witnessed the world's first recorded solar flare. Now, this created a huge geomagnetic storm so huge that it gave dangerous shocks to telegraph operators and set their paper on fire, and auroras could be seen from the north as far down south as Hawaii and El Salvador. And it lasted for about a week. And you weren't just seeing little faint auroras in the sky. You could see bright, rare red auroras. This was a huge thing. And if this were to happen today, it would affect us much worse than it did back then because of how much our society relies on the internet and phones to communicate. If it were down for a week, then it probably would have been worse than Snowmageddon. Overall, auroras are just beautiful and extraordinary. They're complex and they're just really interesting displays of light that are just floating in the sky. If you just think about it, evolutionists will say that wasn't created, but if you look at some light show that you could see what's producing the light, they'll say that was designed, but this wasn't. And I just think it's really amazing. And before anyone asks, yes, there are auroras on other planets.
Oh.
This is a picture of the UV light given off by the auroras from Jupiter. And there are even aurora on Saturn, Uranus, and Neptune, which is crazy because those aren't even, we're relatively close to the sun compared to other planets, but these planets are way farther out. And the fact that they're also getting the same effect due to the solar storms is just amazing. And it's just really complex and interesting, and if it wasn't created, if this was all by chance, then it would have been like 1 in a billion or greater. But it has to be created, and I honestly think that they're really interesting, and I hope you learned something from this presentation. If anyone has any questions, they may now ask them. Yes?
How did it reach the other planets?
It passed the Earth and kept going. I told you that the solar wind, it accelerates them super fast, and so they can continue to get pushed by the solar wind all the way to the outer planets. and also there's not really any friction in space because, I mean, all the gas is like located around the planets, and so that means that if you threw something in space, it might just keep going and never stop unless it hits something. Yes.
Could you read your thesis statement for us?
Auroras are naturally occurring phenomena that create beautiful floating light shows in the sky. Yes.
You said this was UV light,
Yes.
so we can't actually see that unless we have the UV light on.
Can auroras hurt planes flying in the area?
I don't believe so. I mean, it's not like there's gonna be very much wind.
No, I mean
No,
electricity
there might-
wise.
And Joey, it's not that big of a deal because you're probably never gonna see a plane flying that high unless it's delivering a spacecraft up out of the atmosphere.
If a plane drove or flew through an aurora borealis on Earth,
It's not likely
At the
to ever
North
go
Pole.
up that high. Aurora borealis happened in the ionosphere, which is in the lower, exosphere, all through the thermosphere, which has hardly any the exosphere has hardly any air molecules at all. The air molecules it does have a lot of energy and high temperature, but there's not that many.
So planes fly below where this
Yes,
occurs?
They fly like
In the stratosphere?
They fly in like the mesopause,
okay,
the
well,
stratopause.
if they can mess up telegraphs, which are on poles on the ground, and mess up with signals with that, and mess with signals for internet.
I don't think so because the Carrington event was a huge geomagnetic storm. It was very strong,
Okay.
and now we have insulated wires, or better insulated anyways.
Okay.
It probably small ones like they happen all the time. There's a spot on Earth where you can see them almost half the days of the year, but it doesn't really affect the rest of the world.
So that one that he saw just happened to be unusually big.
Yes. Yes.
Why did you keep using your mouse? Why didn't you just click space? Because it's right next to you.
So I don't have to turn around. I don't know.
That's not part of it.
Judah, do you have a question about auroras?
Yes. Can it destroy a rocket ship passing by?
I don't believe so, but it might be able to if it's strong enough. I mean, there was in a video that I saw I didn't use this for my presentation, but there was a NASA spacecraft and it went and flew up into an aurora to gather information.
Oh, cool.
So I imagine that it probably will be all right if the aurora isn't too big. And one more thing, earlier I said that the auroras, they were so powerful in the Carrington event that they could be seen down as far as El Salvador and Hawaii. Well, that's because in periods of large geomagnetic activity, the auroras expand away from their poles and cover more area, but in periods of low geomagnetic activity, you have the opposite. Then they shrink towards the poles or just might not even show up at all.
All right, thank you.